right. Hello. I'm gonna try to present DatDot. It's a spontaneous talk with thrown together slides, so many things can go wrong, but let's see how it goes. I will start by giving a little bit of context. So basically, let me read that. The internet is broken, and we're using it to access and distribute all of human knowledge. Data monopolies hold and enclose upon personal and public data sets, threatening control over one's data and universal access. To tackle this problem, we joined forces in that ecosystem and in collaboration with researchers, librarians, activists, scientists, artists, and civic technologists developed technologies built for peer-to-peer sharing. Anyway, okay, let's continue. So there's that ecosystem which has a lot of apps that are already working using peer-to-peer technology, so they don't rely on big tech and servers, but instead they connect computers peer-to-peer. That's the environment in which we are. That ecosystem has actually the 10 years anniversary this year, and there's many apps that already work, but things are not perfect. There are a bunch of problems, and this is what this talk is gonna be about. So first of all, a little bit about what does it even mean peer-to-peer. So we have the centralized model where we have the one big server or company, whether that's Facebook, Google, or Amazon, and it will talk to all users and connect them, and it can see everything and sell our data and do all kinds of horrible things. So therefore, what if we instead communicate directly? Like maybe Alice can talk directly to Bob, and also we can all talk directly to each other, and we don't need the evil servers anymore. So how does that work? So in that ecosystem, basically that means using Hypercore protocol, which is a protocol to synchronize peer-to-peer data sets without any servers involved. What does that mean in detail? So this slide might take a bit longer. So this particular slide shows 3 computers. They all connect to the peer-to-peer internet. I'll talk a little bit about what that means in a bit. But they are basically 3 people, Bob, Eve, and Alice, and they all use a chat app. So let me zoom in maybe. So the chat app is just a bunch of messages. But what does it mean in terms of datasets? So in DatDot, in order to do what we do, it's very important to understand how the datasets work. So basically, we have here little diagrams. They have some colors, and you can imagine every colored block is a message that somebody sent. So all the messages form an append-only log, so there's always a new message happening after the previous message. And then across all the messages of a single user, there will be something that is called a Merkle tree, which means we fingerprint or hash every message to get like a log of hashes. And then we always take 2 neighboring hashes and build a fingerprint or a hash of that. And we do this all the way up to have only a single root hash, and that one will be signed with a key pair, like an electronic signature. So every user does this with their own chat messages, which means here's the example of 2 messages written by Alice, and those arrows represent that this is meant to be 2 messages, and maybe those other messages are just from a different chat room. And then of course there's this Merkle tree built over that. But at the same time, you can also see messages from, what were they called again? Eve and Bob. So they also have similar message logs, and of course in order for Alice's UI to display those messages, Alice first has to copy the logs from Bob and Eve. But it doesn't have to synchronize all the messages. It's enough if it just syncs the messages that are referencing maybe Alice's messages, or they are from a certain time interval that actually Alice is interested in displaying. So in this case, there's just 3 messages, so she only synchronizes those 3 messages. And in order to do that, she literally asks peers in the network who happen to have those messages to send it to Alice. And once she receives the messages, she also will form those hashes by basically creating a fingerprint from each block with a standardized algorithm, and then also request a bunch of more hashes so that she's able to build part of that Merkle tree, and then compare it with a signature that is supposed to be signed by the private key of, in this case, Bob, and in this case, Eve. And if that's the case, then Alice can cryptographically verify that those messages are actually have been sent by or created by Bob and Eve. And then the UI is just displaying the messages from 3 different logs, the one from Alice, the one from Bob, and the one from Eve. And Alice can then see that kind of chat interface. So the same thing, of course, happens for Bob. The chat looks a little bit different because, of course, Bob will see his messages on the left, but Alice will see her messages on the left. So it's the same content, but it's slightly differently displayed, and the same for Eve as well. So that's basically what those hypercores are. They are cryptographically verifiable append-only logs that can be replicated across the peer-to-peer network. And then an app is just a view that composes the data from one or more logs, depending on how many other peers join the conversation. Yeah, and the replication happens over the peer-to-peer network, which I will now explain. And that's all the foundation for how DatDot works, because DatDot solves a particular problem. But maybe there's a question.
Who would be those peers that, for example, Alice retrieves Bob's messages from?
Right. So the good thing is, because Alice and Bob and Eve, they have what is called a key pair, a cryptographic key pair, a public and a private key. That's like cryptography that was already invented in the 1970s and exists since then. And that's why Alice can retrieve the logs from Bob from anyone, which means she could retrieve it from Bob directly or from anyone else, because once she retrieved all the data, she can use this append-only log and the cryptographic Merkle tree and the signature to verify that this data actually came from Bob, because it's signed, electronically signed by Bob, and that's basically not, nobody can fake this or interfere with this. So she can get the data from anyone, so which means Bob, but maybe Bob is currently offline, but maybe Eve, who's also in the chat room, has a backup or a copy of Bob's data, because she was earlier online when Bob was online as well. And then maybe Alice just connects to Eve and retrieves Bob's and Eve's data from Eve. And the Merkle tree and the signature makes sure that Eve cannot send false data to Alice, because Alice will be able to verify that the data matches the electronic signature, which could have only been created by Bob. So there can be many computers, and if there are many computers like Bob's, Eve's, and many others that have the data, how are those computers discovered, and how is this replication process actually happening? That's what I will explain next. On the next slide. Does that? Okay, so let me see. Right, great. So there's this peer-to-peer network, which is just like a little green circle. But what does that actually mean? So it means there is something called a DHT, which is a distributed hash table. It's a key value store that is not stored on one single database or computer, but it's actually stored across many computers. So how does that work? I'll explain it a little bit, maybe not go too much in depth, but a little bit at least. So every time somebody, like let's say Eve or Bob or Alice or any of the many other computers that join the network, the peer-to-peer network, the first thing that will happen is they will contact some well-known bootstrap servers. Those could depend on the kind of app that they're using. So in the previous case, this would have been a chat app. And then once they connect to the initial peers, they will retrieve more peers or more addresses, in this case IP addresses of other peers in the network, and start connecting to more and more peers. And then, of course, Bob and Eve and Alice, like everyone else, they have IP addresses, but they will also be assigned an address within this peer-to-peer network. And the way this works is Bob essentially, to simplify it, will hash his own IP address, and the hash, the fingerprint of his IP address, is the address in that peer-to-peer network, in this DHT network. And then other peers will challenge Bob and to try to figure out if Bob actually can receive data that is sent to his IP. And if he can solve that challenge, then peers will believe that Bob has this IP address and the hash will be his address. So now, why is this a circle? Of course, a network is many computers connected in various ways. But the thing is, every address, once it's hashed, can be represented in any kind of format. It could be, for example, a hexadecimal string, and then you can sort them alphabetically. And then you can just start with the first one, let's say that's all A's, and then comes B's and C's, and you just put them in the circle based on what is your address. It's kind of random. It's based on your IP address, but you will end up being somewhere in this ring. And now the next step is, if anybody is gonna upload any data to this distributed key value store, the data can be hashed as well. And then all the hashes for any piece of data, whatever that might be, can be compared to the addresses. And if any peer's address, here's an example. So there is a log, in this case would be a hypercore. That's the data structure that I mentioned earlier, this log. Every log has a key pair, or this electronic signature, with which one can verify that the log has not been tampered with. So the fingerprint of that key pair, this value can be compared with the addresses of people, because there are also hashes. And if a discovery key is alphabetically speaking very close to the addresses of those three nodes, or this particular node, then those three nodes are supposed to store data for that topic. And the way this is used in this DHT is that there's only one function. I mean, you can use this for many things, but in this particular context, it's just used for one thing. If you are interested in a certain topic, which just means a certain piece of data that you hash, and that's the address that you're interested in, then you can tell the network, please store my IP address as a value to this particular key. And whatever the key is, then there will be some nodes that are supposed to store that. And then, of course, they will only store it like for maybe 10, 15 minutes, but in that time, any other peer can say, for that particular address, please network, give me all the IP addresses of peers that listed themselves in the network. So hence, I can publish my IP address to the network, and everybody can look up the current list of IP addresses. And once I have the IP addresses, I can try to connect directly to those peers. And the idea is that if there's a data set, for example, this app has those logs, this is the data set that make up this conversation history, then there will be some sort of topic, and all the IP addresses of all the peers in the chat will be listed. So if I know the topic, I will just ask the network, give me all IP addresses that are currently interested in the topic, and then I just try to connect to them, and hence I can communicate directly to them. So that's kind of roughly how it works.
Why do I use this specific system and not just store this mapping from data topics to people who have the data in one place?
Why not just store the mapping from, sorry, can you?
Why do I store it in a distributed hash table? Like
Instead of, for example, where?
I don't know, anywhere in one place on a server.
Yes, so the idea is in the peer-to-peer network, or let me go back maybe a little bit further, we want to get rid of the evil servers and connect directly, but if we do it directly, then where's the data? Usually it's in the server database. We go to Facebook, Facebook gives us everything. So now I need to get the data from elsewhere.
Is this distributed
Hash
hash
table.
table? Is this part of the hypercore?
So DAT, which is what I call it, is basically a lot of things, and historically hypercore is one module that you can JavaScript. I mean, not even one module, but like let's say one module with dependencies that is basically an append only log with a Merkle tree that you can use. So that's kind of it looks like this if you would try to visualize it, but that's just one building block, and you can use it without the peer-to-peer network, and you can use the peer-to-peer network without those hypercore logs. But they are often used together because they make a lot of sense for certain use cases. But yes, they don't. This is usually called hyper DHT or sometimes hyper swarm, and that's the peer-to-peer network. And hypercore is the like the most basic data structure. That's network independent. The most basic data structure, but then there have been more sophisticated data structures that have been built on top of hypercore. So they're using hypercore as a dependency because an append-only log is a very, very basic and simple data structure. And sometimes you want something more sophisticated, like a database that can do a little bit more than just append things at the end. But you can either use this or the other. That's like a part of that or the philosophy in that particular ecosystem, that things should be as modular as possible, and they should do or solve one problem well, and then you can combine them with other modules to solve your particular use case or problem.
So we can call this module as hyper
Swarm.
swarm.
Yeah.
And that is the project built on these two dependency.
Yeah, those are basically maybe the main core building blocks, the hyper swarm or hyper DHT and hypercore. I would say those are like the main ones. They of course have some dependencies, like for example Lipsodium to do the cryptography. But yeah, maybe those are the main ones. So now there's one third part to it. So one thing is the DHT. I can publish my IP address to a topic. I can look up all the IP addresses that are interested in a certain topic. And once I know the IP addresses, I can connect directly to it. So this DHT has one more interesting factor, which is kind of a detail, but also kind of an important one. Sometimes because of the lots of firewalls on the internet and network situation where you can't really directly easily connect to another peer, every node that joins will automatically be interrogated to figure out whether they are having a static IP address or are easily reachable in a network, or where are they positioned, maybe behind the firewall, but maybe they're behind the firewall together with some other peers that are also behind the same firewall because they use the same internet service provider. And the idea is if peers cannot easily connect directly from IP to IP, then those other nodes will try to help them to establish a direct connection. Maybe that goes too much into detail, but that technique is called hole punching. And that's one main focus when working on HyperDHT, that the hole punching mechanism should be as good as possible. And there's a lot of effort that's being put into making this as reliable and good as possible. But once I have my IP addresses, because I looked up all the IP addresses of a certain topic, and then maybe the network helped me to hole punch or connect directly to those other peers. So now I have a direct connection. Those connections are noise end-to-end encrypted. So it's a secure, cryptographically secure connection. And now I want the data. How does that work? So there is another part, that's the hypercore protocol, and I already mentioned it in parts. I can now, there's like a 5 to 10 message types where I can basically, like writing letters back and forth. Like I can first, when I connect to the list of all peers, all the IP addresses for a topic, and I have like maybe 10 connections, then I can just send letters to all of them and say, I would like to have the data for this chat. and then everybody peer will reply based on the topic and my question. Okay, I'm having those ranges of data, and once I receive those messages, those are tiny messages, I can then say, okay, this peer said they have the chat history messages, let's say 100 to 200. Maybe there's 500 messages in the chat history. And another one has only 10 messages. And then my computer, once it receives these messages, can then choose, okay, peer number 5, send me those messages from the chat history. And peer number 10, send me those. And that's basically like a little bit of a back and forth to try to synchronize all the messages of the chat history that you want, and then use those Merkle trees and those signatures to verify that those messages also are not tampered with. And that's sometimes called the hypercore protocol. Yeah.
What if on my phone I use this thing and I've already downloaded some messages, and let's say on my computer I have downloaded some other messages? Would they then exchange the missing parts, if you will?
Yes, they would, but of course they have to be online at the same time. So, but if your phone is online and you're also online in the chat, then they would exchange, yeah, and they would synchronize. Which also creates one problem that you often have in peer-to-peer networks. If you go online and currently no other person in the chat is online, then you can't synchronize any messages, even though those messages might be on the computers of those peers, but they're currently offline. So sometimes the data is not available, but if you wait long enough, maybe they come back online and then you can synchronize. But this can sometimes be a problem, and that's already that's one of the core reasons why we try to work on DatDot. But I first wanted to introduce those basics. Yeah, so next slide. Okay, that's just the same thing in more detail, like basically even with JavaScript code snippets. So that's a little bit of code how you create the hypercore, and then basically how you join the hyperswarm, and here how you join a topic, and then you can listen for connections, and once you have connections, here you can basically write some code that replicates those hypercores. But and here on the other side is Bob that does basically the same thing, but otherwise we just talked about all of that already. So maybe we can just go to the next slide, which is right. So why do we need that hosting network? When Alice is offline, she can find seeders who can seed data on her behalf. DatDot network pairs customers like Alice to seeders who offer their service and their storage to the network. Seeders' job is to store the data on their devices and serve it to interested readers. All right, so basically DatDot is even more than that, because it actually has 3 parts, which is the hosting network, which is what this text snippet just tried to introduce. But then, because this hosting network requires that all apps use hypercores, because if the apps, whatever a chat app uses something else than the hypercore or some data structure based on hypercore, we can't really use our network to verify data and find seeders. It's very important that they use hypercores. But most people didn't write their apps using hypercores. Therefore, we also have like a little bit of a playground or developer environment that is supposed to make it easy to create apps that use hypercores. And another thing is when people create apps, we don't want them to create apps the way we currently have it in that ecosystem, where we have, these are like 8, but we have maybe almost 20 apps. They all use hypercores, but every app does it a little bit differently. So they store this somewhere on disk, but we don't know where the data is. You can, of course, go into the source code and check and find out, but if you're not a developer, you basically can't. And the problem is we need to know the addresses of the data sets, and we need to somehow enable the users to say from all their apps what data they want to maybe keep available. And those apps at the moment don't offer that data to the user easily. So therefore, we came up with the concept of a data vault. So no matter which app, all the data would come from the user's data vault. And the in-browser editor would make it easy to show people how to build apps that use such a data vault, because that's kind of needs to be part of the process of building an app. It's hard to add on later on.
Yes, I had a question.
Mm-hmm.
If I was one of those if I have a hypercore based app,
Yeah.
and maybe I am well, yeah, as you said, the identity management is slightly different in all of them, but outwards on the network and on the wire, they all look like hypercores. Does that mean that I have native support for DatDot, like the hosting nodes?
Yes.
I don't really need to change anything in my app at all. I just need to find some hosting nodes that I can ask to duplicate the data for me.
If your app already uses Hypercore, then theoretically, the same as all .ecosystem apps, you could just use .dot. But the question, and if maybe you can take care of this as an app builder to somehow add a new feature to add Hypercore .dot support for your app. But even if you don't add support for .dot into your app, then a user could take the addresses of the data sets that your app creates and just use them with .dot. The problem is your users might not know those addresses because your app might not expose it. And that's currently the case with most ecosystem apps.
I see. So if like most efficient way would be if there was like some easy plugin that I could like add into each hypercore app that here spend some dots and get your data pinned.
Maybe. Hard to say. I guess it depends on how the app is built. Maybe it's easy, maybe it's not. I assume it shouldn't be too hard, but it's hard to say. Maybe some people came up with really weird ways of building with hypercore that might make it difficult. I don't know.
Of course. No, I was
But
just
yeah, it
curious.
shouldn't be too hard.
Cool. Thank you.
All right. So next would be, so we have like some UI. So the idea is every time you use an app, you would the wallet part is maybe half important. So the wallet part is not is important for using a network like DatDot, which is the hosting network, because that is based on a blockchain. So you might need a wallet aspect to actually do transactions. But otherwise, you have a data vault, which is an app that you use to log into an app. So instead of going to any new app and say, okay, I'll sign in with, I don't know, Facebook, or I'll sign in with my email address, you would sign in with your data vault. And the data vault is basically a URL. And ideally, this URL is something that is just saying localhost. So it's an app that you run on your system. You don't need any servers. On mobile, this could look like this. Maybe I'm coming to some sort of an app. It's just a static website. And then there will be some sort of input field where you enter your wallet address usually, and you connect with your wallet. And that would be a very similar flow to just connect with your data vault and just enter the address. There can be different scenarios. There could be computers that run some sort of an operating system that does it. Or if not, we have a page on dat.org. Maybe we can quickly open that. Dat.org. In this case, it's not done yet, but like it's basically like some sort of an operating system, or not operating system, a desktop experience. And you could maybe open multiple apps, and then all the data that is created when you use those apps, maybe it's a text editor, but it could also be a social network, that's going to be stored in your data vault. And on your phone, you would maybe also connect locally, or you could connect to your laptop or to some maybe external data vault. So what the data vault does, data vault is a process. It has a website with a URL that you use to log in, but the server behind it, not the server, but the process that is ideally running on your local machine as a program that you installed, actually has those 4 different nodes. The wallet daemon is not really important because that's part of the blockchain. But the vault daemon takes care of your data. The hypernode would take care of any peer-to-peer connection. So you have a basically peer-to-peer network connectivity. And the .dot node is a special node that you don't need unless you want to use the .dot network to make your data available in this by maybe paying other peers. If you don't want that or need that, you don't even have to run that. Okay, that's saying the same thing, but just in a different slide format. That's also saying the same thing. So you have a web page that is running an app, another web page which is running your data vault, and you log into one of the web pages with the other one. So these are both web pages running in a browser. And then the web page that represents your data vault, so that's this box, that talks to your local host process, which runs those daemons, like the peer-to-peer network daemon and so on. So this is how it could look like as a simplified way for when you use an app. So let's say you have like 6 apps installed, plus maybe add another one. App number 2 is some sort of chat, and this one would be a quick overview over your data vault. So there's 3 data sets involved, 3 of those logs, one from Bob, Alice, and Eve, and the view just displays you this data in a meaningful way, and then maybe you can also set permissions or maybe withdraw permissions for this particular app to have access to your data set. Okay, it's very simplified, but yeah, that's the same thing, but like in black and white. Okay, right. So then the next part would be that was kind of a little bit about the user data vault and how things work. So the next thing is the playground if you want to build apps. So our idea is you just write here some HTML, JavaScript, CSS code and generates a UI, but you use some sort of an API to connect to the data vault. So when you do that, of course, you have also maybe some sort of a little bit of a log or console that shows you some output. But the data vault is down here, is more like a data vault simulator where you can create like Alice, Bob, Eve, or however many users you want. And then based on your code, data will be created or read, and then you can click around in your app and actually see what's happening. And here basically some permissions that you can give or take away. And you can see what your app is doing.
Why is there a simulator, and what's the difference to the actual data vault?
The difference is basically just that the simulator allows you to create like multiple users. So you would have basically like 3 or 5 vaults for Alice, Bob, and Eve, and then you can switch which one is active to act basically on behalf of all the users in parallel, and maybe even script that to basically see a little bit how your app would work. While in practice, you would probably only have your own data vault and not the ones of others. But otherwise, they're basically the same, yeah. Okay, that's the same thing. Maybe, yeah, in black and white. And then the last part is the hosting network. So, all right, let's say you already built a bunch of apps and they're using hypercores and they connect to the peer-to-peer network, and that all kind of works. But now the problem is because you have a chat app with like 5 people, but they're all offline, and you come online, you want to see the new messages, but there's nothing. So you write a bunch of messages, then you go offline, but when they come online, nobody has your messages, so they can't read what you wrote. That's annoying, so therefore you could use DatDot network, either to help keep your messages available, or maybe you can also just make a backup. Like you encrypt all your data and you make a backup. So in case your computer dies and nobody has a copy of your data, at least you have that.
Yeah, question.
Yeah.
So how do I interact with the peer-to-peer hosting network, DatDot network? How
Yes.
do where do I input the hashes I want?
Oh, all right. So basically there's an app. I don't have slides for that, but basically this is just the same as any app that you could build with this simulator technically. DatDot is also just yet another app that you can use, and then you can go to your data vault and give access to some or all of the data sets to the DatDot app, which will then help you to host it. But of course, you can also technically script it and just interact with the DatDot network directly, but we plan to have some sort of app, and this would be just the same as a chat app or any other app, and you just decide if you give access, and then you have like some UI that helps you do that. That's the plan.
Yeah. No, I was just wondering, but there is no web page where I can go right now. Just input my hash.
No,
I'll
not
see
yet,
them,
but like
collect my wallet.
we have maybe okay, Nina has a demo running, and we have some wireframes, and do we have an app actually already for this?
API access, I understood.
There we have
Between-
API access,
Yes,
yeah, and we
thank
have
you.
wireframes for the app that they're basically finished, but we haven't implemented the app UI yet. That's next. But you can technically already clone the code, run it on localhost, and try in the simulator, and you can script against the API. Right. So now, how does that even work? So the idea is when you have a peer-to-peer hosting network and it's running, and the first thing that you would start with is you have some sort of sponsor. So in case you want to host your own backup, then you would probably be the sponsor for your own dataset. But if you want to host Wikipedia or whatever, then maybe there will be many people who would be supporting it. So technically, any dataset can be supported by nobody, by some, or many. If nobody supports the dataset and you anyway submit it, if the storage network has enough capacity, like enough people offer storage, it will just get hosted. But if there's more and more demand, and at some point maybe there's not enough storage space for all datasets, then those people who actually sponsor a dataset because they have some tokens, they will probably slowly squeeze out those that are just hosted for free. But as long as there's enough storage space, everything gets hosted. So when the sponsor comes and sponsors a dataset, there will be seeders who would maybe offer their storage to the network, but they might just do it because they want to get some tokens or earn something for it. You could build your app in a way that you kind of make a mechanism that all the participants of that app or friends host things, so you don't run in this problem. Usually if there's like a popular dataset, you don't even need the DatDot network, because the same as BitTorrent, your data will always be available. But if you deal with the dataset like your personal backup, okay, maybe if you have lots of technical friends, they might just host the backup for you. But like people who don't know many people, they might have a problem. So now they're paying a Google or Apple cloud, and then they could just use this network instead.
Also, for my data to be available at my friends, they would have to run their nodes, have them be permanently online, right?
Yes.
So it's not like a phone with a reduced battery and connection and so on.
Yeah, I mean, or if they don't run it all the time, maybe then you would need to call them or like, I need my data, can you put your computer online? So there might be ways, but like maybe that's not reliable enough for some people, so they want to make sure and have like some additional backup, fallback or whatever. And the DatDot network, what it does is basically it connects sponsors with seeders. So sponsors can publish datasets and sponsor them, or they just publish datasets and sponsor them, but then the sponsor can also already sponsor existing datasets that are already known to the network and maybe improve or add to the redundancy. Like it's already sponsored, I sponsor it even more to have it even more redundantly stored. And the seeders, they just basically get told by the network after they register it and say, I have storage. If there's some data to store, I'll be up for it. And then there's a matchmaking algorithm that runs every interval and matches all the requests for data hosting with all the offers of storage. And the way that works is, I think that's the same thing. Yeah, so kind of it works as a marketplace. The way that works is there's multiple phases. Like if there is a data set that has been requested or there was a request for hosting and sponsors paid for it, and there's also a node that offers storage, then and they are matched, then there will be those are called events. So the blockchain in every block emits events, or every block is anyway replicated by all nodes, but then every node scans for the events in that block and checks if any of those blocks references that particular node that got the copy. Like I wouldn't scan, but like, of course, if I registered for, I have storage space available, then every block that comes in, I would scan if I was mentioned to host some data. Mm-hmm.
Well, those events would be, please store data X for me.
Yes.
Or delete data X. You don't need to store it anymore.
Yes. Or I mean, there's the delete works in the way to say, from now on, you storage, the hoster that offers the storage, the blockchain will just say from now on, the blockchain is not going to pay for this anymore. So therefore, I don't know, maybe they'll just keep it, but like they won't get rewarded for it. So they probably just drop it. Also, the way the DatDot network does it is if there's a data set, it will split this. At the moment, the default is in ranges of 10 chunks or 10 blocks, and then selects multiple peers for every range of 10 blocks to redundantly store them. So you probably, if you offer storage, you get like from many different data sets, small parts of it. You very unlikely have like an entire data set that you store. You would probably always only store like certain small parts of a data set, but from many data sets. That's how the matchmaking algorithm does it. And the first part is the hosting setup process.
I have another question.
Yeah.
This matchmaking algorithm, it is not being run in one place, right? Because you want to eliminate single places where things are being organized and therefore power concentrated.
Actually, it is run in one place, but that place is always changing. And that's basically based on the blockchain. So we have at the moment, I think, just the default. So we're using a substrate framework, which helps to make blockchains, and they have a bunch of modules for different consensus mechanisms. And at the moment, we're just using the default proof of stake mechanism that comes with this. We could use proof of work or some other mechanisms. And then every time some node is based on that mechanism selected to produce the next block, they would run the algorithm to do the matchmaking. And then in the next round, the next miner that produces the next block would do it again. But if they feel the previous one would kind of didn't do it well, then maybe they can also build on the block that was before. And that's the whole point of like, how does a blockchain work? Which branch do we follow? The longest chain, like in Bitcoin, for example, the longest chain is always the one that wins.
So if I understand correctly, this is the idea is to prevent that someone would just coordinate seeders and sponsors.
Yes,
in
that's
a wrong
extremely
way.
important, yes. Because if we don't do that well, if there's a way to influence this, then the whole point of rewarding people with tokens for hosting or for doing anything could be hijacked, and people could just basically essentially print money for themselves. And that's, of course, what we want to avoid, which is also when I use the DatDot network, I cannot select who will host my data, because the person hosting my data, if they do it successfully, they will earn something. So if I can manage that my own computer will host my data, but then I earn token for this that I can use to pay others to do even more stuff for me, that's not really what we want. So yeah, so now from now on, these will be the details of how technically the DatDot network works. I can go into this. I just wonder if there are questions, or would it make sense to continue into those details? Is there some interest? I mean, I would like, basically that's based on how we do verify that this all works, even though it's decentralized and all that stuff. All right. So as soon as as soon as the matchmaking matched a sponsored data set, and the sponsored data set means any data set that is based on hypercore. So for example, there are key value stores. One is called Hyper-B, another is called Hyper-Tree. Then there are file system-like data structures like Hyperdrive. And there has been like other experimental data structures like a blob store, and also some more high-level databases, but they all use hypercores. So, and which means it doesn't matter, like the DatDot network doesn't need to know whether it's a Hyper-B or Hyperdrive, whatever is the data structure, because underneath it's all hypercores. So these are just basically usually the operations that somebody recorded when they interacted with whatever database or data structure it was. And a key value store, like add this key, delete this key, maybe if there's a rename operation, I don't know. And those things just get recorded in a hypercore. So if I replicate a hypercore, I can replay those to get the same state of my database. So if the DatDot network chose, okay, you are, we call the hosters seeders, you are those 3 seeders, and we now and the DatDot network emits an event and says, seeder 123, you're gonna host data set so and so, and because this data set, this hypercore has like 10,000 blocks, you're gonna host blocks 890 to 910 or something like that, which is just 20 blocks of, and of course 3 copies, because all 3 seeders are supposed to join the peer-to-peer network and download the same 20 blocks from that particular hypercore and then keep it available. And this whole process, this hosting setup, goes on in parallel many times over. So there will be other seeders, 1, 2, 3, that are also assigned for the same hypercore, but instead of block number 890 to 910, it's maybe block 910 to 930. And then basically have like this hosting setup process for this particular feed goes on like 100 times in parallel. Every time it's 3 different seeders, 3 different encoders, 1 attester, and they all are reading the event. Okay, for this hypercore, I'm supposed to download these 10 blocks and then keep them available.
That's a quick question. So the redundancy number is like minimum 3.
Yeah, minimum is 3, or let's say default is 3 that we're using at the moment. But when you, as a sponsor, make the submit the request to the chain, there's a configuration file where you can configure all kinds of things that we completely ignore at the moment. But you can set the redundancy. You can even say what kind of latency do you want, is the geographical region, what's the time, and there's like loads and loads more parameters that we defined. And in the future, we try to incorporate all of that into the matchmaking, but at the moment we ignore it. Yeah.
If this matchmaking happens in parallel,
yeah. So basically,
how do you make sure that a seeder doesn't get assigned more hosting tasks than they can actually fulfill?
yeah. So the blockchain keeps track of that. So if there's like the blockchain knows who's currently assigned for what and how much storage space or capacity do they have and how much was already assigned to them. So they're kind of keeping track. The blockchain keeps track of that to not overload a peer.
So it might be that one of the 100 processes has in fact they together, like the parallel runs have in fact overloaded a seeder, and then one of them will fail, like the last one.
Unlikely, because for each seeder individually there would be some sort of a balance sheet or whatever that the network, the blockchain is keeping. Like seeder number 5 currently has 10 hypercores assigned, and those are the ranges, and this is the amount of storage space that all of that takes, and this is the amount of storage space they said they have, therefore there's so much left, and based on this I can assign them more or not. But of course, if a seeder somehow in between, I don't know, was gaming a little bit and somehow something filled their disk space, they might not have that disk space, so which means once they are assigned, they would probably start failing the challenges, which would then be a signal to the network to say, okay, we reduced the reputation, maybe try again, but at some point the network would emit a new event to assign a new seeder to download a copy from the remaining seeders, because there's of course redundancy, and then take the job away from the seeder because they failed the challenges. So yeah, if somebody fails because they don't have the space, the network is trying to replace them, basically. So now we have, so the event includes also an attester and encoder, and why is that? So if there are 10, let's say the range, there's a hypercore with an address and it has 100 blocks, and 10 of those blocks are supposed to be seeded by seeder 1, 2, 3. So if they do that later, there is a problem, a very general problem, because of course there's 3 seeders and they all seed the exact same range, which means if anyone wants to download or test them, if they have those blocks, one of those seeders could just say, every time they get asked, oh, please give me block number, I don't know, 5, they would say, oh yeah, I'll do that, just wait a moment. Hey, you people, other seeders that see this, can you give me block number 5? Yes, okay, here it is. So they basically don't do any job. They just like free write on the remaining seeders. And if every seeder does that, then there's no hosting. But as long as at least there's one, then it would work. But the problem is if this one peer then goes offline, the other seeders don't even have a copy. So that's what we want to prevent. So we want to make sure that every seeder actually stores a copy and not just free writes on those who actually do the job. And this was a little bit of a tricky problem, but we found an interesting property of the Broadly algorithm, which kind of helped us solve this problem. So we were talking to the people that came up with Broadly, had like a little bit of email conversation and interviewed them and checked, and it turns out that there seems to be no way to make Broadly deterministic. So you can compress data, and if you decompress, you get the same data, but the compressed data, there's no guarantee that it will look the same. Usually it always is a little bit different. That's just the way Broadly works internally. And this seems to be a property that can't really be changed. So you can almost rely on it, and that's pretty cool. And then there's another property of Broadly that is also quite convenient, and that is when you compress Broadly, there's multiple levels of compression, and I think the highest is kind of level 11. We use the highest level, I think it's 11 or something, but maybe it depends. But the point is compressing data takes quite a long time compared to decompressing it. So we just want to, but then there's also another problem is, it seems that when you have the compressed Broadly data, you can't see by looking at the data what level of compression was applied to it. So we just say there would be 3 encoders, and their goal is to compress each block with the highest compression level and then sign that. And then because we don't know because of course an encoder gets rewarded for doing that, but they could just compress it with level 1. We can't use the block to actually figure out if they did compress it with the highest level. So therefore, every encoder that does basically the same job sends those blocks first to the attester, and they always compare for, if the range is block 1 to 10, then they receive 3 times block 1 from 3 encoders, and they just compare sizes. And if they are approximately the same, we just believe that they probably used the highest compression level, and if not, then the encoder will not be rewarded. Mm-hmm.
This means that both the encoder and the attester will have the amount of traffic of all the data that is being stored compressed, right?
Yes. So, I mean, seeders have to download the data and can receive it. So basically, instead of receiving it directly, the encoders receive it directly, then it goes to the attester, and then it goes to the seeders. So it takes that kind of little bit of a, I don't know, extra journey.
Maybe what is also important to mention that the same as seeders were selected randomly, for this task also encoders and attesters were selected. So they're not like always the same attesters.
So the block,
they're also random.
There's a palette or a module in the blockchain that's already available in Substrate. There are many actually. They are called verifiable random generators. I don't know. Anyway, we're using them to do this random selection. And there's researchers who try to come up with those. There's some papers like about the properties, and yeah, they're basically those implementations. They're supposed to generate randomness in a distributed way, so that you can kind of rely on that it's random. So we just trust that this works. The framework does that. So once you receive this as an attester, and they are all kind of approximately the same size, they get forwarded to the seeders, and the seeders receive them, and they say, okay, I received all the blocks. And then the attester will, after every block has been encoded and forwarded to seeders, submit like an answer to the blockchain, a transaction, saying, okay, the hosting setup was successful, but if in between one of the encoders maybe doesn't do their job, or the blocks when the attester compares them, they're not the same size, or he forwards them to the seeders, but the seeders don't respond, there's many conditions in which this might fail, and then this has to be repeated. But if it, and then nobody gets rewarded. But if it works out, then everybody gets a reward according to the task. So encoders have more CPU and traffic. The seeders also have some storage, and the tester doesn't have to produce the blocks, just compares it, has a little bit of less CPU going on, but like we didn't exactly define how much effort each task is, because that's kind of what we mean by reward. We just basically record for every encoder, a tester, seeder, for every type of job, how much CPU, RAM, memory, whatever traffic they approximately used or in this process, and that's what we do. It's not really accurate, but we kind of rely that every block is something like 64 kilobyte on average, and we just kind of think that like the effort of encoding is an average kind of the same. They will be approximate numbers, maybe we have to tune them. Anyway, so if this hosting setup is successful, then the blockchain will, based on that, trigger the next process, which will be, that's the same. That's also the same. That's also the same. That's again still the same. Yeah, iterations. Okay. So yeah, then there will be, so now, okay, technically the seeders are supposed to have the data and they're supposed to seed it to the network, but they might not, and we have to make sure that they do. So in regular intervals, we send basically like in Deutsch, in what is it, in the trains, you have sometimes people checking if people have tickets. So we do kind of random checks, and we basically check, like we sample basically if they have the data, and if they don't, they lose reputation, which means they're getting less reward for storing. And if they always pass their checks, they gain more reputation, which means they will get more reward. So people basically always successfully manage to do their challenges. They might get a better reward, a reputation, and then earn higher rewards to motivate them to make sure that they're reliable, ideally. And we have two kinds of checks. So one we call the proof of storage, which means a tester again is selected to go and check hosters, many hosters actually, for certain kinds of chunks, which means they go connect directly to them using the peer-to-peer network and tell them, all right, please send me blocks number 5 for this hypercore and block number 10 for this one, and even multiple ones. But they have to not send them the normal one. This is some sort of a protocol that has nothing to do with the regular hypercore, because the way the seeders that actually are part of the DatDot network store data for hypercores is not like they don't use normal hypercores. They use hypercores that we changed a little bit. Basically, every time a block comes in the beginning, when they receive that block from those encoders, basically, those are compressed blocks, and those we store in a key value store based on the index in the log, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, in a compressed form. And we rewrote or basically added an extension to the hypercore module, so that every time the hypercore tries to follow the regular logic of replicating blocks from the hypercore, the protocol will ask a specific peer with a hypercore to send them block 5, 6, 7. And we intercept that. And when we notice that the hypercore wants to try to get 5, 6, or 7, we go to our key value store, take the compressed blocks, quickly decompress them, and then give it to the hypercore to do its job of replicating. But if the tester connects, we basically, based on the index of the block that they want, we just take it directly, the compressed block, and send it to the tester. And when the tester receives it, they can check, based on the original hosting setup event, who was the exact peer or the encoder that was responsible for giving to this particular hoster the block. And then they look up the signature, and compare this compressed block to the signature of the encoder, which is something that the hoster cannot create because they don't have the encoder's key pair that did it. And that way we make sure, because every hoster, even though there's multiple ones that store the same block from the same hypercore, they will all have slightly different compressed versions of those blocks. So the signatures are different. And this is how we make sure that basically they have to store that data. And the only way how they could otherwise recreate the data, they could maybe keep the signature from the encoder, but drop the block. But then when they get challenged, they would need to, in real time, download the block from someone else and then compress it with broadly in the highest compression level and hope that the output is kind of what matches the signature. And it probably doesn't, so they have to do this multiple times, but the compression with the highest level in broadly takes quite a long time. So they might not be able to do the challenge on time, so it's easier to just store the block. So that's kind of the model that the currently assumption that we do. And based on if they can produce the block and the signature matches, then they will get rewarded. But that just makes sure that they have the data, and they will provide it to an attester that asks them to give them the compressed data. That's not something that happens on the normal peer-to-peer network, because there is no such thing as a compressed block. That's not part of the hypercore concept. So they could still not serve the data. They have it on their disk, but they don't serve it to peers. So we have to have another check. So, okay, that's the same. That's the storage challenge. Proof of storage. Here's the format, how that looks like, but okay. So we have not proof of delivery. Okay, it's called proof of performance now. In the beginning, it was called proof of delivery, which is like, do they deliver? Do the hosters deliver blocks to some normal peer-to-peer peer or a reader that wants the block? But because we're not just checking if the hoster provides the block to anyone who asks for the data, but we can, in the same process, also measure the latency and throughput and lots of other measurements. We renamed it to proof of performance instead. And that data will later go on the blockchain, and it will be used, it's not now, but in the future it will be used to improve the matchmaking, to select peers based on their latency and maybe region and all that, so we can optimize things, but we don't do this at the moment. So it's called proof of performance, where an attester joins the swarm and just starts downloading random blocks and pretends to be like a normal peer, like an undercover train controller, or I don't know how to get the checking tickets, whatever. And measures in the same time, okay, how fast do those hosters or seeders respond, and do they actually provide the blocks, and that kind of stuff. That's the same thing. And after they downloaded some blocks, they have to, then they reveal themselves and ask the hoster to sign the latest blockchain event. And that's what basically the attester then provides back to the chain, so the chain can verify, oh, they got an actual signature from the hoster, so they at least were connected. And then and of course, there's not just one attester that randomly checks, but multiple ones, so the chain can compare the results from the multiple random attesters, because they all check, maybe somebody didn't do their job, but the attester only gets rewarded if they get this signed event from the hoster, and the hoster is motivated to give that signed event to a connecting attester, because the hoster knows only if the attester provides that to the chain, then the hoster will get rewarded, otherwise not. So that's why the hoster and attester are both motivated to connect and get that signed event and provide it to the chain, including the rest of the challenge, and then the chain can even compare the results from different attesters. And that's the proof of performance, to in regular intervals, to make sure that hosters are providing the data to the peer-to-peer network, and also measure performance to optimize the matchmaking once we include that data in the matchmaking process. Yeah, that's, I guess, it. And then we have, of course, a little bit about DatDot tokenomics, which, oh yeah, here we have actually screenshots from the app from DatDot. It's a little bit messy. It's not also the latest, but basically you can select the address of the hypercores that you want to have hosted. There's an API for all of this, but just if you want to use the UI, then you can select the chunk ranges, because each address is an append-only log, and there might be many chunks in that, so you can select those. Then you can select the time from when to when it should be hosted. And of course also a geographic region you can select, or multiple. And then you basically customize, we're calling that a plan. And then when you define your plan, there's even another part, like a performance. You can say something like how much redundancy, what are the latencies, and you can configure a whole bunch of more things. And when you did it, then you can see an overview over all your plans that you currently sponsor, like data sets that should be kept available by the DatDot network. And you can see how much you're spending on those plans, how are they performing over time. That's kind of like a little bit of a dashboard that makes you see that. You monitor the data sets. And then if you are on the other side, if you're somebody providing the storage to the network, you can see all the data sets that you're currently hosting, and you can see a list of events, whether you succeeded or failed for a certain challenge. And if you succeeded, you earn some tokens. And here you can basically see over time, maybe even filter, for which data set did you succeed or fail challenges, and how did you earn. And the tokens that we have is storage. So there's a storage token. We just basically record, you stored 1 gigabyte of data for 1 month. So that's kind of what we record. You could call that a token or not. I mean, it's not really a token, but that's kind of what we record and what we treat as tokens. So storage, how much storage did you provide to the network? How much CPU, how much memory, how much download, how much upload. I think latency not maybe, but yeah. And then you have here, you can see also, you can see it in bars for the moment, for the current moment. So you can click around here to change that and scroll around, and maybe we'll adapt that, but that's kind of the idea. Have also a little dashboard of where you see how you perform.
This is available already?
No, so the APIs are available to do all of that, and the wireframes are available, but we didn't implement the app for it yet. What we did implement is like a little bit of a desktop looking like website with a little terminal, which is not completely wired up, but the idea is you could then either in the terminal execute against the API of DatDot to host data sets or publish them. And later maybe you can have like a little command, whatever, not npm install, but something to get actually this kind of app and launch it inside of here, and then you can also click around. This is implemented, but the DatDot app is what we currently started to work on. So the implementation is work in progress. Right, and then here exactly in the terminal you would maybe type something like npm install, or maybe you would type dat install, I don't know. Something would run through, you install a bunch of modules. And now what you can do is, at least for apps or anybody who would make an app. So for example, the Pico editor that we saw earlier in the previous talk, or our DatDot app, or many other apps that people might hack together, they can, if they want, define a little configuration file, which might be part of the package JSON or a separate file. And the idea is that the project or the repository or the app would have some sort of address, probably not Ethereum, but maybe like a DatDot address. And then they would define a cap, which means how much tokens or amount or whatever units. It's very likely not be anything else than those DatDot tokens that I mentioned in the beginning, but who knows, in the future maybe more, because the framework we're using allows us to technically also use other kinds of tokens that have nothing to do with our blockchain. And per month, so which means if this particular app or project somehow gets rewarded with so many tokens in this month, then after that amount is reached, it won't get anything else until the next month starts. So you can have kind of artificially set like a maximum for yourself. If I get 10K a month, I'm happy, I don't want more. But you can also say I want 20 or whatever, it is up to you. I don't know how people will use this, but the idea is that there is a maximum. And then what you also will do, you will set the list of contributors. So these are all the people that maybe work with you on the module, app, whatever the software or data set is that is described here. And then you can also set all the dependencies. So maybe data sets might have dependencies, maybe apps will have dependencies, many software has dependencies, so you can, for each of those dependencies, define a share. That's just a number. So by adding up all the numbers, you get the total amount, and then you can, based on each individual dependency, see how much percentage it has in terms of shares of the total amount of dependencies. Same for the contributors. So there's 3, 4, 13, that's like what, 20, right? Yeah. So 20, so which means this one has 13 of 20, this one has 4 of 20, this one has 3 of 20, it's also kind of a percentage. And then there's a ratio, and the ratio just means how much of any income that you get will be distributed amongst the contributor, and then the remaining part will be distributed amongst the dependencies. But if your project has reached this cap, then everything will go to the dependencies. And if they also reach their cap, then everyone, so it's basically packages, data, apps, modules, whatever you have, will be skipped as soon as they reach the cap, and it will go to the rest. And if all projects in this supply network reach the cap, then the person trying to donate will be refunded, and maybe also people who donated earlier will be refunded. And if you want to contribute, then here is a little bit of a link where you can either just have some text, what are the conditions if you want to work and help to work on this particular project. But this could technically also be a smart contract that manages this address. So these are kind of the thoughts that we have around that. And this is a little demonstration of the DAT ecosystem. So we visualized, and we might have a talk in the next days about this. So this is basically the DAT ecosystem. So there are the consortium, the DAT ecosystem consortium has currently 6 or 7 members, and there is a manifesto, and there's many rules that have been written down, and this includes a list of blessed modules. For example, Hypercore is a blessed module, and some others, and all the other bubbles in there are either dependencies of Hypercores or other modules, or dependents. So anyone who's using Hypercore, or people who use stuff that is using Hypercore, that's all indirectly in there. So it's the whole supply network. And so you can see when you hover some of those modules that are in there, and they're all kind of around DAT and Hypercore and all the projects that exist in the DAT ecosystem. And of course, somewhere in the middle, there's also Hypercore itself as a module. Let's see, will it be selected? I think it will be selected at some point. Yeah, StreamX is, oh no. Was it already there? Did we skip it? I don't know. But yeah, so this is the idea, and every single of these packages will potentially have some configuration file like this. And that's how, and the idea is every time you will have anyone in the DAT ecosystem, every time somebody, will install anything here, but if that person also has an income, because they're a seeder in the DatDot network, so they're earning some money or some tokens, then a fraction of those tokens that they earn, if they earn something. If they don't earn something, then not. But if they earn something, then based on all the stuff that they have installed, a fraction will be distributed amongst this supply network based on those configurations. Right, and these are the same things that we've had earlier. So the hosting setup, proof of storage, proof of performance. This is what people earn for, and if they earn, but they also happen to use software, then a fraction of their earning will be automatically distributed through the supply network based on the configurations of all projects. So that's kind of tokenomics. You pay for having datasets hosted, you earn for offering storage, and some redistribution happens based on what software and datasets you actually use, and the distribution is basically defined in those configuration files of each individual package, where you have this whole network of packages. And that's kind of it. I think that's all of it. So there's no more.
Cool.
Yeah.